I'll talk briefly about the difference between random and systematic error. And then the three main types of bias. I'm going to focus on selection bias and information bias because you have a separate lecture from on bias and confounding by Manolis, which is next Thursday of next week. And I'm not quite sure where in the course you'll learn about DAGs, directed acyclic graphs. I have some slides at the end just out of interest, but I'm not going to use them. I'm going to focus on more conventional methods of talking about these types of bias. But my standard set of slides on this topic has some on directed acyclic graphs, so I've just left them in there just in case they're of interest. So random and systematic error. Random error is not unique to epidemiologic studies, and it also occurs in randomized trials. So, you know, suppose I have a drug that, just like if I toss a coin, on the average, I would expect to get 50 heads out of every 100 tosses of the coin. But in practice, very rarely will I get exactly 50 heads. I might get 48 or 45 or 52 or 60 because there's essentially random error, or at least factors that we don't have enough information on, which means that we can't exactly predict what happens every time we toss a coin. And it's the same time when we do a randomized trial. Even if we're trialing a drug that doesn't work, it might do slightly better or might do slightly worse than placebo just because of chance, random error. And it's the same in observational studies. Even if there's no confounding and no other biases, we might just see a chance association in a particular study. So the disease might be more common in the exposed than the non-exposed group. Now, how do we deal with random error? Well, basically, we deal with random error by doing a larger study. So if I toss a coin 100 times, I might get 55 heads and 45 tails. That doesn't mean there's a bias or a problem with the coin. It just probably means there's a chance variation. If I toss a coin 10,000 times, I would expect to get very close to 50% heads and very close to 50% tails, because the larger numbers mean that these random variations essentially cancel out on the average. So if I tossed a coin 10 times and I got 7 heads and 3 tails, wouldn't worry me. If I tossed a coin 1,000,000 times and I got 700,000 heads and 300,000 tails, it's probably something wrong with the coin. And assuming there's nothing wrong with the coin, then as I toss it more and more times, the percentage of heads will get closer and closer to 50%. So the precision or lack of random error of an effect estimate is reflected in the 95% confidence interval. And random error reduces and precision increases as the study size increases. So random error is always with us, and we can never eliminate it completely, but we can reduce it by doing a larger study. Systematic error is different. Systematic error occurs if there is a systematic difference between what the study is estimating and what we're trying to estimate. So there's some sort of bias involved. It means it's like the coin is inherently biased, so no matter how many times I toss it, it's going to come out with 70% heads rather than 50% because there's something wrong with the coin. It also occurs in clinical trials, but some types of systematic error may be more likely to occur in epidemiologic studies because of the lack of randomization of exposure. So the key difference is that to minimize random error, we can do that by doing a larger study. But if there's something wrong with our study design, if there's some inherent bias, then doing a larger study won't solve that. We need to do a better study. We need to change the design of the study or the way we analyze it to overcome that bias. So that's the fundamental difference between random error and systematic error. The first one, just do a bigger study. The second one, doing a bigger study won't help you. You need to actually do a better study and change the design or change the analysis. And these types of systematic bias really fall into three groups: selection bias, information bias, and confounding. So let's suppose once again, we have a population and we're comparing exposed and non-exposed over a risk period. If you look in the textbooks, you can see lots and lots of different biases that people refer to, but they really fall into three groups. We have a population followed over a period of time, and we select the participants from that population. So we select them, and maybe they agree to take part and maybe they don't. So selection bias is any bias arising from the way that study participants are selected or select themselves from the source population and time period. Second thing we have to do is get information on them. So we find out who's exposed and who's not exposed, who has the disease and who doesn't have the disease. And we can make mistakes with that. So we can have misclassification of exposure or disease, and therefore we can have information bias, which is any bias arising from errors in classification of the exposure or the disease status of the study participants. And finally, logically, confounding actually comes first, but in practice, we try and deal with it in the analysis. So because in observational studies, the exposure has not been randomized, confounding can occur if, because of the lack of randomization, the underlying risk of disease is different in the non-exposed groups. And that's actually a property of the source population. Maybe the people who work with asbestos smoke more than the non-exposed people who don't work with asbestos. So that's inherent in the population. And it's something we have to try and minimize or adjust for. So confounding is an inherent property of the population we're studying. But once we've defined that population in that time period, we select people and we get information on them. And all of the different biases we can think of come into one of these three categories. And I'm going to focus on the first two categories in this talk. So selection bias, by this definition which I've just given, if we define the population and we're doing a cohort study or incidence study, so we're following everyone over time, and we get 100% response rate and we don't lose anyone, then you can't have selection bias. You may have other problems, but if you just study everyone and they all agree and you have information on everyone, then selection bias is not a problem. However, what you often find is that you don't have 100% response rate, and some people are more likely to participate than others. For example, I do a lot of asthma prevalence surveys, and it often happens that people who have asthma are keen to participate in the study, and people who don't have asthma don't have the same motivation. That in itself won't necessarily produce a bias, but if it's also related to exposure, so asthma cases who have a particular exposure are more likely to participate than other people, then you get a selection bias. There's a particular problem in case control studies, which I won't go into here because it'll come up later in the course. What's the solution to selection bias? Well, the best thing is just get a response rate of 100%. And in the case control study, ensure that controls are a random sample of the source population. So that's the best thing, is just prevent it. If you can't avoid it, then you can try and control for the determinants of selection bias. For example, often in surveys, there's different response rates by age or different response rates by socioeconomic status. And that can actually make age or socioeconomic status into sources of bias, even if they were not sources of bias in the original source population. So for example, if exposure doesn't vary by age, the percentage exposed is the same in every age group, but you get lots of old people who agree to take part and lots of young people don't agree to take part, and it's also related to exposure. So young people who are exposed maybe take part, young people who are not exposed don't take part so much, then you'll get a selection bias. But you can control for that to some extent by controlling for age. So you can control for the determinants of selection bias as confounders in the analysis. And if you can't do that, you can at least try and assess how strong the selection bias might be. So those are your three solutions in general. Avoid it by getting a 100% response rate. Control for it because some of the determinants of selection, like age or social class, essentially become like confounders, even if they weren't confounders in the first place. Or just try and estimate how big it might be and how strong it might be. So that's all I'm going to say on selection bias, except that there's some additional issues in case control studies, which I won't go into here, but the slides are here if you want to have a look at them. Information bias occurs when there's misclassification of exposure or disease. And the misclassification can be random or it can be systematic. So if the misclassification of exposure is not related to disease, then the misclassification is non-differential. So maybe we misclassify people, but it's essentially at random. So the misclassification rate in those who get the disease is the same as the misclassification rate of exposure in those who don't get the disease. So if the misclassification of exposure or disease is unrelated to disease or exposure, then the misclassification is non-differential. On the other hand, if the misclassification of exposure is related to disease, then the misclassification is differential. And an example of that might be if you're doing a cancer case control study and you've got cases of cancer and you ask them about things like pesticide exposure. If you've got cancer, you've probably thought quite a lot about what might have caused it. So you might remember that your neighbor sprayed some pesticides in their garden 10 years ago and some of it drifted across to you when you were sitting outside having a cup of tea. And if you're a control, you're healthy, you may not have gone through the same thought process. So the cases might actually remember all of their past exposures, whereas the controls might remember some of them, but not all of them. So that would be an example of differential misclassification of exposure. So let's look at non-differential a bit more. So here's a study. We have 100,000 people or person years, and we follow them over time, and maybe we get 100 deaths in the exposed. And in the non-exposed, it's 10 out of 100,000. So the incidence rate or death rate is 100 per 100,000 here. The non-exposed, 10 per 100,000. And the true rate ratio is 10 times. So that's the truth. That's what you would get if you did a perfect study. But of course, we're never going to have perfect data, so we're going to misclassify some people. So let's assume that 15% of the exposed are actually misclassified as non-exposed. So they're really exposed, but we get it wrong. We think they're in the non-exposed group. And then in the non-exposed group, let's say 10% of them are wrongly classified as exposed. We think that they're actually not exposed, but we think they are exposed. And you can see these are quite low rates of misclassification. We're probably better than we would get in most occupational studies. And I also assume that misclassification is not related to disease status, so it's non-differential. So what do we see when we do the study? Well, we have 100,000 exposed people and 100 of them have died. And for 85% of them, we get it right. So 85%, 85 out of 100 deaths are correctly classified as exposed, and 85,000 person years out of 100,000 are correctly classified as exposed. But for 15% of them, we get it wrong. So there's 15 deaths out of 100 that we wrongly classify as non-exposed. And there's 15,000 deaths out of 15,000 person years out of 100,000, which we wrongly classify as non-exposed. So the red ones here are those that are really exposed, and some of them we get it right, some of them we get it wrong. And then in the non-exposed group, remember 10% of them we misclassify. So 9 out of 10 deaths we get right, but one of them we mistakenly classify them as exposed. 90,000 out of 100,000 person years we correctly classify, but 10,000 we get wrong. And we classify them as exposed, even though they're really not exposed. So what do we see when we do the study? we think that in the exposed group, this 85 plus 1 is 86 deaths out of 85,000 plus 10,000, which is 95,000 person years. And the death rate or incidence rate is 91 per 100,000, 86 over 95,000 times 100,000. In the non-exposed, we think there's 24 deaths, there's 105,000 person years, and the death rate or incidence rate is 23. And the rate ratio is 91 per 100,000 divided by 23 per 100,000, which is a rate ratio of 4. Now remember, the real answer was 110 and the rate ratio of 10. And we've only had a small amount of misclassification. We got it right 85% of the time for the exposed, but 15% we got wrong. And we got it right 90% of the time for the non-exposed, but 10% we got it wrong. And that's, even with that small amount of misclassification, the rate ratio has gone down from 10, which is the true number, to 4, which is what we see when we do the actual study. So the bias, now in fact, what would happen if our exposure measure was complete rubbish? It was just like tossing a coin. Then we would actually end up with the exposed group, supposedly exposed group, really being a 50-50 mixture of exposed and non-exposed. And what we think is the non-exposed group would be a 50-50 mixture of exposed and non-exposed, and we would get a rate ratio of 1. So if we had perfect exposure data, we would get the right answer of a rate ratio of 10. If we had completely hopeless exposure data, we would see no difference between the groups and we'd see a rate ratio of 1. Because we've got reasonably good but not perfect exposure data, we get something in between. And the bias is always towards the null value of 1. So the bias is towards the null, so the relative risk estimate is biased towards 1. And therefore, if we find an association between exposure and disease and there's non-differential misclassification, then the true relative risk is stronger. It's further away from the null than the actual observed relative risk. So typically what happens is you do the study, and there's two things you always get criticized for in occupational studies. One is there's probably confounding, which we'll deal with later in the course. And second, people will say your exposure data is not very good. But if we've done the study well, and we know that any misclassification of exposure is going to be non-differential, it's essentially random. So the deaths get misclassified at the same rate as the person years. And we've still got an elevated risk. If we see an odds ratio of 4, we know the right answer must be greater than 4. Because any misclassification would produce a bias towards the null. And therefore the real answer must be further away from the null. So it must be greater than 4. So it's one of the things that drives me crazy in occupational studies, that you always get criticized for having bad exposure data. But if you've designed the study well, so that any misclassification of exposure is non-differential, then, and you've still got an effect, then you know the real effect must be even stronger. You mainly worry about non-differential misclassification if you get a rate ratio of 1, and then, or close to 1, and then you really don't know, is it really not elevated, or is it just not showing much effect because the random misclassification is so strong. There's a couple of exceptions to this. If the specificity of case ascertainment is 100%, but the sensitivity is less than 100%, then the risk difference will be biased towards the null, but the relative risk will not be. So suppose we start again with, this is the truth, but for some reason we only find half the deaths. Maybe all the death records were held in two large buildings, and one of them burnt down, and they lost all of those, and they only found the records in the other building, and it was essentially at random. Well, there's 100 deaths here, but we'd only find half of them, so we'd find 50. And there's 10 deaths here, but we'd only find half of them, so we'd find 5. So we'd get something like this. And actually the incidence rate, now the real answer would be 100 per 100,000 and 10 per 100,000. We get half that, so the rate difference is actually 45, whereas the real answer is 90. But actually the rate ratio is still 10. It's just 100 times a half divided by 10 times a half still gives you a rate ratio of 10 times. So if you just miss a few of the cases or deaths at random, but you're looking at ratio measures, it doesn't actually cause any bias. So that's one exception. The second thing is that if there are multiple exposure categories, then bias may be away from the null for some categories. So let's go back to our example. This is what I called exposed, but it's now high exposure. And this is what I called non-exposed, so it's now low exposure. And then this is really non-exposed. So this might be the factory down the road, which doesn't involve the chemical you're studying at all. And then within the factory you're studying, you may try and classify as people as high exposure and low exposure. And of course, you will make some mistakes when you're doing that. So let's suppose, like before, that 15% of the highly exposed people were misclassified as low exposed, 10% of the low exposed people were misclassified as highly exposed, and the non-exposed, it's easy, they're in the factory down the road, the chemical is not there, you get that correct. And once again, misclassification is not related to disease status. So these are the right numbers, as you can see, and these will stay this way because we get the non-exposed group correct. But this group, there's some misclassification. Some of the high people go into the low category by mistake, and some of the low exposure people go into the high exposure category by mistake. Then we'll get something like this. These are the same numbers as I showed before, but we're now comparing them to this non-exposed group. So before we had a relative risk of 20 times versus non-exposed and 2 times versus non-exposed. Now we actually get 18.1, which is a bit less than 20 compared to non-exposed. But in the low exposed group, we get 4.6, and the right answer was 2 times. So it's actually gone up. And that's not surprising because the low exposed group is really a mixture of mostly low exposed people, but a few high exposed people. So you get a higher rate ratio when you compare them to the group with no exposure. High exposed, they're a mixture of high exposed and some low exposed. So you get a reduction. It goes down from 20 to 18. And you can often see this in occupational studies where, for example, when you're doing SMRs and you're comparing an occupational population to the general population, you see an increased risk. But then when you look within the exposed factory, you don't see much of a dose response, or you see a less of a dose response because of this random misclassification of exposure within the factory or within the workforce. The third exception is that if there is misclassification of a positive confounder, then control for that confounder will only partially remove the confounding. So there will be bias away from the null compared to what would have been obtained with full control of confounding. So let's suppose that we do a study and the crude odds ratio is 4.0, 4 times. And then we want to adjust for smoking. And it's unlikely, but in this hypothetical example, this elevated risk of 4 times is entirely explained by smoking. So if we adjusted for smoking using the methods you're going to learn in the rest of the course, our main exposure odds ratio would change from 4 to 1. So the smoking adjusted odds ratio would be 1.0 if we had perfect smoking data. But in practice, we're not going to have perfect smoking data. It's probably based on questionnaires. It might be okay, but not perfect. And therefore, when we adjust for smoking, we won't remove all of the confounding by smoking. So instead of the main exposure odds ratio going from 4 to 1, it might go down a bit. It might go from 4 to 3 or 4 to 2 or 4 to 1.5. But it's not going to go all the way to 1 if we don't have perfect smoking data. So in that case, the smoking adjusted odds ratio will be biased away from 1 because we haven't managed to completely control for confounding by smoking. Here's an example from a study I was involved in on paracetamol and asthma, which was published in The Lancet a long time ago. And it was paracetamol use early in life and asthma at age 6 or 7. And the crude odds ratio for paracetamol, now let me fix this now because I keep sorry, let me just, that shouldn't say smoking, it should say confounder adjusted odds ratio. So we had the paracetamol effect was about 1.8 times, but if we adjusted for a bunch of things, it went down to about 1.4. And we had a big argument about it because some people really think that paracetamol use causes asthma. But I thought, on the other hand, that almost half of the excess goes away when we adjust for confounders. And we know we haven't controlled for all of them, and we know we don't have perfect data on them. So it probably would have gone further down towards 1 if we'd had better confounder data. So that's why I would always show the unadjusted and adjusted effect measures, because it's not just a matter of adjusting for confounding and seeing what happens. It's a matter of what direction did it change in? How much did it change? Would it have gone all the way down towards 1 if we'd had better confounded data? So that's non-differential misclassification. Differential misinformation bias, the bias can be in any direction, so it can be towards or away from the null value. So it's usually desirable to ensure that information bias is non-differential, even if this means not using some of the information on one group. So it's important to collect the information in a similar manner in the groups being compared. That's why, for example, in randomized trials, we usually do them double blind, so that doesn't mean we get better data. It just means that any mistakes are going to be at random. They're not going to be biased by knowing which group the participant was in. An example of non-differential information bias, I mentioned before that cancer patients may recall pesticide exposure, even if they just had a very small exposure many years ago, whereas healthy general population controls may be less likely to recall brief exposures. And this would produce a bias away from the null in a case control study of cancer and pesticide use. So I'm not going to talk about confounding because that's going to come up in later lectures. But so I'll just skip through these slides, but you're welcome to look at them. But I would wait until Manolis's lecture on bias and confounding, which is Thursday of next week. But just to summarize, when we design a study, we really want to do 4 things. We want to reduce random error by making the study as large as possible and through appropriate study design. We want to minimize selection bias by having a good response rate and by selecting controls appropriately in a case control study. And we want to ensure that information bias is non-differential and keep it as small as possible. And we want to minimize confounding in the study design and control for it in the analysis. And we only need to do these 4 things perfectly, and we have a perfect study. But the point is that these things are actually in competition. So, for example, often you might do a large study with a questionnaire, and someone will say, questionnaires are no good, we should have taken a blood test of exposure. And often the blood test of exposure won't be any better anyway. We'll talk more about exposure actually on the 5th of October. But even if taking a blood test gave you better exposure data, it probably means you're going to have a much smaller study because you can't afford to do a large one. So you're going to have more random error. And also some people won't like giving a blood sample. So you'll have a lower response rate. So you might reduce information bias, but you might increase random error and increase selection bias. So study design always involves a compromise between these issues. So for example, obtaining better exposure information may reduce information bias, but may reduce random error if the study size is thereby reduced. 2 other points to finish on. I say confounding is often weaker than expected, that's very context dependent, but in occupational studies, usually confounding is not such a big issue. It's a much bigger issue in maybe studies of lifestyle, like, you know, nutrition, or whether people smoke, or whether they take vitamin E tablets. But in fact, occupational exposures, particularly when we're comparing with other blue collar workers, usually this confounding is fairly weak, because it's essentially random depending on whether someone starts work, or if they're allocated to one section of the factory or another section of the factory. And also, non-differential information bias cannot usually cause false positive findings. Okay, so I'm going to stop there. And are there any questions or comments on any of those factors? Like I said, well, if you want to ask me about confounding now, feel free, but I'll mostly refer you to Manolis's talk next week.